Hello again. Today we're going to be looking at section 1.2 out of the book on row reductions and echelon forms. So let's start off with a couple of definitions. First off, a non-zero row or column in a matrix. Now, when we're talking about matrices, we're going to be dealing with matrices through most of this course. So when we talk about a non-zero row or column in a matrix, it's simply a row that has a non-zero entry in it. So in this example, we have the first three rows are non-zero rows. They have something in them other than zeros. That fourth row is a zero row. We're going to be talking more about rows than columns through this course, so we'll be dealing mostly with non-zero rows and zero rows. The second definition is a leading entry. So when we talk about a leading entry in a row, we talk about the first non-zero entry in a non-zero row. So in this matrix that we have a leading entry in the first row, we have a leading entry in the second row, and we have a leading entry in the third row. So that's the definition of a leading entry. Okay, so the next important definition that we're going to look at is row echelon form. Now, spoiler alert, what we are going to be doing in this course is we are going to be taking a matrix, a coefficient matrix, which we saw last class. We are going to be doing elementary row operations with the goal of turning it into a matrix in row echelon form. So this definition is very important because this is the end goal of a lot of the techniques that we're going to be learning in this course. So what is row echelon form? We say a matrix is in row echelon form, or simply echelon form, if it meets three conditions. First, all non-zero rows lie above zero rows. So any row that's totally zero, they all have to be at the bottom of the matrix. Secondly, the leading entry of every non-zero row lies in a column to the right of the column containing the leading entry of any preceding row. Okay, that's a bit convoluted, but really what it means is that as you move down the rows in your matrix, mark off the leading entries. The leading entries have to keep moving to the right as you go down the rows in your matrix. The third says that if you have a leading entry in a column, then everything below that leading entry has to be a zero. So let's look at a couple of examples. Here's a couple of matrices. So first off, we're going to mark off the leading entries in every non-zero row. So if we mark these off first, then it gives us a bit of a better idea of what's happening. So we had three conditions. So the three conditions were, first off, that the zero rows at the bottom. So do we have that? Do we have the zero rows at the bottom? Well, on the first matrix, yeah, we do. There's a single zero row, it's at the bottom. The second matrix doesn't have any zero rows, so it does still satisfy that definition. The second condition says that the leading entries move to the right as you move down the matrix. So leading entries move to the right. Does that happen? In this first one, yes. You can see as you move down the columns, the leading entry keeps moving to the right. What about the second one? Well, the second row has the leading entry in the third column, but then the third row has the leading entry in the second column. So no, they don't keep moving to the right, they've turned around and come back left. So as you move down, it doesn't satisfy that condition. What about the third one? Third one says it's all zeros under leading entries. So take a look at all the leading entries and look at everything underneath them. That's all zeros, that's all zeros, that's a zero. So yes, that one satisfies the definition. What about the other one? Well, it's all zeros under that leading entry. The second leading entry, the second column, has a leading entry with nothing underneath it, so that's fine. But look at this one. You have a non-zero entry under a leading entry. So that means that that matrix also fails. So our first matrix is in row echelon form. Our second matrix is not in row echelon form. Row echelon form is very important to understand because, as I said, most of the techniques we're going to be doing in this class, the goal is to get into row echelon form. Now there's another definition, which takes row echelon form and goes one step further. In this class, we are going to be getting to row echelon form, and then we will often try to go the next step to something called reduced row echelon form. Reduced row echelon form has three more conditions. Well, three additional conditions. The first one says that it has to be in row echelon form. The second condition, remember the leading entries. It said that the leading entries for reduced row echelon form have to be 1. They can't be any other number. And thirdly, look at the columns where the leading entries live. This condition says that every entry in that column, except for the leading entry, has to be a 0. Whether it's above or below it, it all has to be a 0. So here's the example. Look at these two matrices. Again, mark off the leading entries. And you can see that both of these matrices, they are in row echelon form. So they both meet the conditions for row echelon form. But now what about the two new ones? So leading entries are 1. Well, not here, because you have a leading entry that's a -1. So that fails. The one on the right does meet that criteria. And then the third criteria says that all entries in columns with leading entries, in leading entry columns, are 0, except for the leading entry itself. So if you look at them here, in the left one, you have all 0s there. You have all 0s in the second column. The third column has a leading entry, but it has something that's non-zero. So again, that fails. But now if you look at the second matrix, there's a leading entry in the first column. Everything else is 0. There's a leading entry in the second column. Everything else is 0. There's a leading entry in the third column. Everything else is 0. The fourth column doesn't have a leading entry, so you don't care what happens there. That meets the conditions. So of these two matrices, the first one is in row echelon form, but it's not in reduced row echelon form. The second one is in row echelon form, and it is also in reduced row echelon form. And as I mentioned, one of the goals of everything we're going to be doing in this course is to take a matrix, perform elementary row operations, and get it down to a row echelon form, and then to reduced row echelon form. So recall from last time, we looked at something called elementary row operations. And when we did an elementary row operation, we took a matrix, did some things on it, turned it into a new matrix. Any matrix that you have can be reduced. We call it reduced when we do enough elementary row operations to turn it into a matrix in echelon form. So we are going to use elementary row operations to turn matrices into echelon form and then into reduced echelon form. Now here's the important concept. When you take a matrix and do your elementary operations on it, you can bring it down to echelon form. Depending on the operations you do, you'll get different matrices every time. So transforming a matrix into echelon form can give you different matrices. But then if you go farther, turn it into row reduced echelon form, you will always come out with the same matrix. This is an important concept to understand for the initial part of this course. So let's look at an example of this happening. So here's a matrix, same matrix twice. We're going to turn it into row reduced echelon form in two different ways. So what can we do? Let's take this first one. Let's first turn row 1, take the negative of it. So negative row 1 becomes the new row 1. That's an elementary row operation. So row 1 becomes 2, negative 3, negative 4. Row 2 stays the same. Okay. Now, let's take the next row operation of row 1 plus row 2 becomes the new row 2. So we're replacing row 2. So row 1 stays the same. Row 2 is the sum of the two rows. So it becomes 0, 2, 4. Now look at what we've got here. We have a matrix in echelon form. Okay? Now, let's keep going and do more row operations to turn it into a matrix in reduced echelon form. So let's take this matrix, take 1/2 of row 1 is the new row 1. What are we going to get with that? I'll continue it down below here. We get 1, negative 3 over 2, negative 2, and 0, 2, 4. So you can see now we have the leading entry in that first one is 1. So we're getting there. What's next? Well, let's take 1/2 of row 2, and that becomes a new row 2. That's the next elementary operation. 1, negative 3 over 2, and negative 2. Row 2 becomes 0, 1, and 2. And now one final operation. We are going to take row 1 plus 3 over 2. Row 2 is the new row 2. What do we get? We get 1, 0, 1, and the next row becomes 0, 1, 2, stays the same. Now look at this matrix. We are in reduced echelon form. Go back and look at the definitions if you need to, but you can see we are now in reduced echelon form, so here we stop. Now, let's do this again. We start with the same matrix, but let's do different operations. Now, this is one of the keys to understand. To reach your goal of being in echelon form or reduced echelon form, there's no one set way to do it. There are lots of different ways to do it. So let's do it a different way. This time we're going to take row 1 minus row 2 is the new row 2. So row 1 stays the same. Row 2 becomes 0, negative 2, negative 4. Now, take negative 1/2 of row 1 is the new row 1. We get 1, negative 3 over 2, and negative 2. Second one stays the same. Oh, what I didn't point out was that after our first step, we are in echelon form. Note that the matrix in echelon form is different from the one that we had before in echelon form. Not a whole lot different in this case, it's just negative, but it is a different matrix. So echelon forms for a matrix can give you different things. So now we're going to continue and try to get to row reduced echelon form. If we take negative 1/2 of row 2 is the new row 2, we get 1, negative 3 over 2, negative 2, 0, 1, and 2. Now this will look very familiar with what we had before. If we take row 1 plus 3 over 2, row 2 is the new row 2, we again get 1, 0, 1, 0, 1, 2. Okay? If you're uncertain about those calculations, go through them yourself. But now we are in reduced echelon form again. And notice we have the exact same matrix above. So here's a key thing to remember. Reducing a matrix, you can always get it into echelon form and reduced echelon form. The echelon form will depend on the operations. You can come out with different matrices in echelon form. If you go all the way to reduced echelon form, you will always end up with the same matrix every time, no matter how you get there. So theorem 1, each matrix is equivalent to one and only one reduced echelon matrix. That's the summary of what we just went over, that no matter what path you take, echelon form can look different. Reduced echelon form will always be the exact same. So a couple more definitions. Pivot position. We talked about leading entries. Those are actually called pivot positions. So the positions in a matrix that contain the leading entries of non-zero rows, we call them pivot positions. All of the columns that have a pivot position, we call them pivot columns. Okay. Now, I mentioned before that there are many different ways of taking a matrix and transforming it into echelon form. The Gaussian elimination method is a method that you can use that will convert any matrix into row-reduced echelon matrix. It does it by identifying these pivot positions, pivot rows, converts pivot positions to 1, and everything else in there to 0. Everything else in the pivot column to 0. Here are the steps. Okay. So I'm not going to read these out. We're going to go through an example of how we do this. But the general idea is that you find your pivot columns, pivot positions, you turn everything in the pivot column to 0, except for the pivot position where you turn into a 1. So now we're going to use the Gaussian method on this matrix to turn it into row-reduced echelon form. So what does it tell us to do? The Gaussian method says, find the leftmost column that's not all zeros. So in this case, we're looking for the leftmost column that's not all zeros. It's the first column. Then it says to take the top entry in it. And what we're going to do is we're going to turn that into a 1 and turn everything else in that column to 0. Now the one step that you have to do sometimes that position will be a 0. Sometimes you have to exchange rows to get a non-zero in there. That's step 2 of the Gaussian method. In this case, we've identified a pivot position. This is it's non-zero to start with. So what we're going to do is we're going to eliminate everything below it. So our first step is we are going to look at all of the entries below that, and we're going to turn them into zeros. So we're going to start by saying row 1 minus 2 row 2 is the new row 2. What do we get? Well, our first row stays the same. Our second row is being replaced by row 1 minus twice that row. 0, -5, -5, and 0. And our third row stays the same. Now we're going to continue. We have our pivot entry stays the same, but we have another non-zero entry under there. We're going to turn that one into a 0 with elementary row operations. So if we do row 1 minus 2 row 3 is the new row 3. Row 1 stays the same. Row 2 stays the same. Row 3 now changes. It becomes 0, -1, 1, and -2. So now we've succeeded in turning everything under that to a 0. Okay, so now the next step is we are going to eliminate the row that we just worked on. So the row that we just worked on, we're going to ignore that row now. And we're going to deal with what's left. So with what's left, we identify the next pivot position, which is the topmost row and the first non-zero column right there. Now we are going to work at getting everything below that equal to 0. Well, there's only one entry below that, the -1, so we have to turn that into a 0. So if we do row 2 minus 5 row 3 is the new row 3, we are going to eliminate that -1 underneath the new pivot position. So we have 2, 1, -1, 2. And for the second one, that stays the same as well. 0, -5, -5, 0. And the bottom becomes 0, 0, -10, and 10. Now, look at our pivot positions. We have our first one, we have our second one. Our third row gives us a new pivot position now. But note that we are now in echelon form. So now that we're in echelon form, what we are going to do is we are going to turn all of the leading entries into ones. That's the next step. So we want to turn the leading entries into ones. So the first leading entry is the first row. It's a 2, so we take 1/2 of row 1 is the new row 1. It gives us 1, 1/2, -1/2, and 1, and the others stay the same. That takes care of our first one. Our second pivot point, we want to turn that into a 1. So -1/5 of row 2 is the new row 2. First row again stays the same. Second row becomes 0, 1, 1, 0. And our third row stays the same. So now note that we have 2 of our leading entries are 1. We just have the final one to deal with. So -1/10 of row 3 is the new row 3. And here's what we get. That's a 1/2, -1/2, 1, 0, 1, 1, 0, and 0, 0, 1, -1. Note that now we've met the second condition of row reduced echelon form. It's in echelon form, and all of the leading entries are 1s. But what's left now is we have to turn everything above the pivot positions into 0s. And we haven't reached that yet. So let's start by rewriting our matrix here. 1, 1, 1, 0, -1. Now, our first one is, we're going to start from the other side this time. So we're going to start from this entry in the third row, the leading entry in the third row, and we are going to eliminate everything above that leading entry, turn it into 0s. So how do we do that? Well, let's take row 1 plus 1/2 row 3 is the new row 1, and we get 1, 1/2, 0, 1/2. Our second and third rows stay the same. Let's continue with that. We have one more non-zero entry above that pivot position. So for this one, we're going to do row 2 minus row 3 is the new row 2. 1, 1/2, 0, 1/2. Now row 2 changes, becomes 0, 1, 0, 1 when you do the subtraction, and 0, 0, 1, -1. So now we're done with that one. Let's move over to the next pivot position. We have one entry above that that's non-zero. So if we do row 1 minus 1/2 row 2 is the new row 1, we get 1, 0, 0, 0, 0, 1, 0, 1, and these two stay the same. But now we are in row reduced echelon form. So this followed what's called the Gaussian method. If you follow the Gaussian method, you are always guaranteed you are going to come out with a matrix in row reduced echelon form when you're finished. So here's another definition: solutions of linear systems. So harken back to the first class. We saw that we had a system of linear equations. We saw how to turn it into a matrix. We've seen that any system of linear equations, you can write it as the augmented matrix that we saw from last class, or from the last lecture. The row reduction method gives us a technique to solve any system of linear equations. So here is the main thing for one of the main concepts for this course is taking a system of linear equations, turning it into an augmented matrix, doing row operations to go to an echelon form matrix. Then from the echelon form matrix, you can read the solution. The solution being the values of the variables that work in all the equations. So here's an example. So the example is this. This is a simple system of linear equations. Two equations, two unknowns, two variables. We can write this in augmented matrix form. The x's, we have an x column, we have a y column, and we have a constant column. So the x's, the coefficients for the x's are 3 and 6. The coefficients for the y's are 2 and 1. And the constants are 5 and 8. So there's our matrix. There's the matrix that we're going to solve. So what we're going to do is we are going to use row operations now to turn this into row reduced form. So what does it say? The Gaussian method says find our first pivot point, turn everything under it into a 0. So if we do 2 row 1 minus row 2 is the new row 2, we are going to eliminate the first number in that column, or the second number in that column. We get 3, 2, 5 for the first one. We get 0, 3, 2. So that eliminates our first one. Now we are in echelon form. So the Gaussian method says now we want to turn our leading entries into ones. So for the first one, we get 1/3 row 1 is the new row 1, which gives us 1, 2 over 3, and 5 over 3, and 0, 3, 2. Now we have one more leading entry that has to be turned into a 1. So if we do 1/3 row 2 is the new row 2, we get, well, the first row stays the same. The second row becomes 0, 1, and 2 over 3. So now we have all of our leading entries being 1s. Now we have to get rid of all the numbers above the leading entries. Well, there's only one case of that. So if we do row 1 minus 2/3 row 2 is the new row 1, we get 1, 0, 11 over 9, 0, 1, and 2 over 3. So here is our row reduced echelon form matrix. And remember what this matrix represented. The first column were the x's, the second column was the y's, the third column was the constants. So we can take this matrix now and we can turn it back into the equations. What do we get? We get x plus 0y equals 11 over 9. We get 0x plus y equals 2 over 3. What does that mean? Well, now it's pretty easy to read the solution. X equals 11 over 9 and y equals 2 over 3. Note this, when you have taken a matrix, converted an augmented matrix, converted it into row reduced echelon form, the solutions are sitting right there in the right-hand column. This is the solution. If you take these two numbers now and put them back into the original equations, you'll find that both equations are equal. Both equations now work with these numbers. Row reduced echelon form gives you your solution sitting right there in the right-hand side of the equation. So let's look at another idea here. The idea of basic and free variables. A basic variable. If you have a column that contains a leading entry, then the variable corresponding to that column is called a basic variable. Anything that's not basic is called a free variable. So here's an example. We have this system of linear equations. 3 equations, 3 unknowns. Turn it into the augmented matrix. You get that augmented matrix. Now go through all the transformations, the elementary row operations, to turn it into something that is in row reduced form. We won't go through all of those, but if you do, and remember it's going to be unique, you're going to end up with this matrix. Now take a look at all of the leading entries, all of the pivot positions. You have one there, you have one there. The third row now you'll note has disappeared. There's no pivot entry in there. So what we have now is we have 2 columns with pivot entries or leading entries. We have a third column without one. So by definition, the basic variables are the ones that have pivot positions. So x1 is a leading entry, or is a basic variable. x2 is a basic variable. x3, the column for x3 doesn't have a leading entry. That's called a free variable. And you can see that summarized right there. The idea of basic variables and free variables. Now, when we have a solution, we can write a solution in what's called a parametric description of the solution set. So we solved the system of linear equations a minute ago. We ended up with something like x equals 11 over 9 and y equals 2 over 3 or something like that. That was a specific solution. Sometimes you end up with an infinite number of solutions. When you have an infinite number of solutions, we can write down the solutions in what is called a parametric description. When do we have an infinite number of solutions? If you have a free variable. So if you have even one free variable, what it means is that you have an infinite number of solutions to your system of linear equations. So of course you can't write down individually an infinite number of solutions, but what we can do is describe all of the solutions by a parametric description. What we're going to do is we're going to say the free variable, let it be whatever you want, then we can calculate what the basic variables are going to be. So let's look at an example of this. Here is a system of linear equations that has been converted into an augmented matrix. So let's say we take the augmented matrix, we do the row reductions, and we end up with this. Notice that that is in row reduced echelon form. So from row reduced echelon form, we can identify now the basic variables and the free variables. So each column, x1, x2, x3, x4, x5, we have 5 variable columns here, and then we have a column for our right-hand constants. Where are the leading entries, or the pivot positions? Here's one, and here's one. So now that we've identified those, we know what the basic and the free variables are. Our basic variables are x1, x2, and x4. Our free variables are x3 and x5. But now note our pivot positions in the equations. So now we've taken the matrix, we've converted it back into equations. That was a leading entry, that was a leading entry, and that was a leading entry. So now notice that all of these leading entries have a coefficient of 1. Everything else in there in the equation is a free variable. So when you are in row reduced echelon form and you convert it back into equations, all of your pivot positions are in the equations a single time with a coefficient of 1. Now we can take these equations and we can rewrite them. So those first 3 equations, so what we're going to do is we're going to write, first off, every variable, x1 through x5, equals something. What do they equal? Well, x1, we can rewrite the first equation to get x1 equals negative 4x3 minus 2x5. So a basic variable equals an equation of free variables. x2 as well, we rewrite the equation, we get a value for x2. What about x3? Well, x3 is free, so we just write it as x3 equals x3. What about our next one? x4, we had an equation for x4 because again, it's a basic variable. So we rewrite it as x4 equals something, 4 plus 4x5. And then our final one, x5, is a free variable. So we just write it as that. So now we have equations for all of our variables written in terms of our basic variables. So we're going to be revisiting this idea of writing it in terms of parametric equations over and over again. Now I'm going to rewrite this again in terms of matrices. So I can take that thing that I have here that I just came up with, these equations, and I can write this in terms of matrices, x1, x2, x3, x4, and x5. That's equal to, what's it equal to? Well, it's equal to some constants plus something times x3 plus something times x5. And what are those things? Well, those are matrices as well that you can take from here. So what are the constants in each of those equations? x1, there is no constant. x2 has a constant of 2. x3 is free. x4 has a 4. x5 is free. What about the x3s? Well, just look at the equations and see where all the x3s are. We have a negative 4, we have 5, we have 1, we have 4, and we have 0. Now what about the x5s? Look in the equations and see where all the x5s are. Minus 2, 3, 0, 4, and 1. So take this that I just wrote, multiply it all out, and you'll see you come up with those equations that I just came into. We're going to do this again later on, but the idea of parametric description of solution happens when you have an infinite number of solutions In other words, it happens when you have at least one free variable. And the idea is to write all of your variables, the solutions for all of your variables, in terms of your free variables. And this is a description of all of the possible solutions. We'll be doing more of these exercises shortly. But all of this stuff together leads us to Theorem 2. Remember we talked about linear system being consistent or inconsistent? Well, Theorem 2 says a linear system is consistent, in other words, it has at least one solution, if and only if the rightmost column of the augmented matrix is not a pivot column. So that's putting it slightly different terminology than what we've been talking about so far. But take this matrix, for example. Say that you row reduce, and you have this as your matrix when you row reduce. Well, this is your X variable column, this is the Y, and this is the constants. What are the leading entries? There and there. Oops, we have a leading entry or a pivot column that is in the rightmost, the constant column. If you have this happening in an augmented matrix, you have no solution. In other words, it's inconsistent. So consistent means that you do not have a pivot column or a pivot entry in the final column of your augmented matrix. The second part of this theorem says that if a linear system is consistent, in other words, if this doesn't happen, if a linear system is consistent, then either there's a unique solution. A unique solution is when you have no free variables, or there's infinitely many solutions when you have at least one free variable. So the free variables give you really important information about a solution. It tells you right away if you have a single solution or if you have infinitely many solutions. And the existence of even a single free variable means you have infinitely many solutions. Thank you for your attention with section 1.2.